So before we going to discuss the naive-Bayes algorithm, we have to study the Bayes rule. The Bayes rule related to event A and B. So these two events can be represented by as the random variable A and the random variable B. So the probability of A given by B equal to the probability of B given by A times the probability of A divided the probability of the B. So in this case, we said that the probability of A given by B can be further written. So for the numerator, we just copy the numerator. However, for the denominator, for the probability of B, we can be further written as the probability of B given by A times the probability of A plus the probability of B given by not A complement of A times the probability of the complement of A. Okay, so these two equations in the block, these two are the same. So we have some applications which is here. So let's let A be the sentence. It is sun shining. Okay, so A describe the sentence. It is sun shining. B describe the sentence. Michael takes a walk outside home. So from here, we have the probability of it is sun shining is 0.3. So the probability of B given by A, which is the probability of Michael takes a walk outside home, given it is sun shining, which you take the probability of 0.8. So the probability of B given by not A, which is it is not sun shining. Michael takes a walk outside, given it is not sun shining, and take the value of 0.2. So we wanted to see the posterior probability of A given by B. So what is the given Michael takes a walk outside home, and okay, so we want to see the probability of it is sun shining. Okay, we wanted to compare this probability. Okay, so in this case, we just plug the formula from what we have learned for the second formula. Okay, so P of A given by B equal to P of B given by A times P of A divided by P of B given by A times P of A plus P of B given by not A times P of not A. Okay, so in this case, since P of B given by A is equal to 0.8, P of A is get 0.3, so P of B given by not A is 0.2. The P of not A, which is 1 minus P of A, is equal to 0.7. So you plug all the values we have obtained, plugged to, okay, so for each of the probability. Now then, we just do the, okay, so we do the arithmetic operations on these values. So finally, we get a result, which is 0.63, okay? So this means the probability of it is sun shining given by the Michael takes a walk outside the home, take the 63% chances, okay? So this is for the Bayes rule application. So we have another example. Last time we already described the joint probability, and we can use the table to, so we have the joint probability. So since we have 3 variables, college degree, is a random variable. So the hours worked is a random variable, and WLC is a random variable. So each of the random variable is a binary random variable. Take the value of 2. So for example, topology degree, take the value of no or yes. So hours worked take the is also, it is a binary variable, and it takes, for example, 2 values. One is 40.5 negative, which is work hours less than 40.5 hours. Another is greater than or equal to 40.5 hours. So still take 2 values. For the WLC, also take 2 values. One is a medium, another is a richer. Okay. So for each of the, it has the joint probability, which is listed on the first columns of this table. For example, the college probability of college degree equal to now the working hours worked equal to 40.5 less than 40.5, and we'll see equal to medium. That probability, joint probability is 0.253122 exaggerate. Okay, so by this table, and we can go further and to do some okay, to compute the conditional probability of P of college degree equal to college given by the WLC equal to medium. Okay, so from here we listed 3 kind of computation for the 3 types of computation for obtaining the probability of the college degree equal to college and WLC equal to medium. Okay, so we can compute by the conditional probability formula we have described in the previous slide, or we can apply Bayes' law and compute this probability of college degree equal to college and WLC equal to medium. So you can go home to do this little bit of practice. So this for these 2 question marks you filled in, so the value will be the same. Maybe it has some little bit of difference after the decimal point, maybe in the start from decimal point from left to the right, maybe in the 3rd digit has a little bit of difference there, which is the accuracy. Okay, actually, basically, these 2 are need to be equal. Okay, need to be equal. So here since we related some machine learning, we related all the data. Okay, we need applying an algorithm on our data set. So first, we have to make the sum. Okay, so we want to represent our data numerically. That one is we want to. Then we can apply this. Okay, apply our algorithms on the data, and we can show our procedures numerically. Okay, numerically. This is what we want. This is our purpose. Now, so in this case, for each of the data instances in our data set, which definitely is a set of variables, random variables. So frequently in the data science, in the machine learning class, we call each of the random variables a feature. Okay, so feature is more focused on from a computer science perspective. For a random variable is more focused on the mathematical perspective. Okay, as long as I state the feature, actually it is a random variable. Okay, in the future maybe I'm abuse these 2 notations actually, which is equivalent. Okay, which is equivalent. Now let me set up the problem related to our data set. Okay, our data set. Now, so a data set consists of a sequence of a data set consists of a set of data instances. Each of the data instances is a sequence of features. Each of the feature in this case, which is represented by X with the subscript. This means this is the position, the feature 1 and the feature 2. Okay, so in this case, X is represented as a data instance. Okay, so in specific, a data instance is represented by a sequence of features. X1 to Xn, so this means you have n features to represent a data instance. Okay, so X is a vector of n Boolean variables, actually, which is Boolean random variables. So in this case, now, so corresponding to each of the data instances, we have a class label Y. Okay, so in this case, Y is equal to Y1, Y2, and Ym. Okay, so frequently we handle the case which is Y, a class label just only have a set of 2 class labels, which is the simple case. As long as we can handle this case for the case, general case, definitely it is easy for us to handle. The one thing I want to say for each of the x's and for each of the y's, it has x, actually I said s for the x. So in the simple case, x is, if I said a Boolean variables, so take the two values, okay? So for the y, actually it is a scalar, okay? So y from here, y1 might be, for example, take the value 0, y2 take the value -1, y3 take the value +1, etc. So if for each of the y's, it is a scalar. For each of the x's, which is a variable. So in your case, even if you already in the homework assignment 1, I already gave you, okay, the data. So in that case, for each of the x's, if you already working on the homework assignment 1, it is not just only x take 2 values, maybe it has a set of values. Okay, set of values. We say you have a set of attributes, okay, for each of the x's. So that way is the difference between the x and the y. Okay, so each of the element of the x and each of the element in the y. Okay, which y is a scalar. Okay, x is a variable. It might take a set of values. Okay, so it is the difference. So what is the task? So our task, we want to approximately define the target function f mapping x to y. What does this means? This means we have a data instance, okay? So for example, we have a data instance. We want to, in the case of we don't know the class label of y for this data instance. So what are we going to do? And we want to, okay, find a function from our data set so that you are given a new data instance that's no y, so the class label y which is missing. In that case, by what we have, okay, so function, we can mapping this x to the corresponding y. Okay, so we can find the class label for this x. That is the purpose we want. Okay, specifically, we want to learn function of p of y given by x. This is we want to find the probability of y, class label y, and the other x given x. So how can you do it? Definitely you have to based on the data in your hand. So by that data, you have changed some parameters to represent that function. So that and later on you can predict the class label of X. Okay. So in this case, we want to design learning algorithms to learn the function based on the basis rule. Okay, so here we have applying basis rule. In this case, we write down the probability of what we are given is X represented by the sequence of X's. Now we want to compute the probability of Y equal to Yi for all I's in Y. Okay, so in that case, by this we can predict the class label for new data instance. So from here we just write down X for the new. So this is new data instance. So how can do it? So we compute the class label. So Y equal to Yi for all Yi's given by X equal to X new. Okay, which is based on applying the basis rule for the in the specific for each of the class for each of the variables. You just put the specific. Okay, so the Xi's and the Yi's in. Okay, so P of Y equal to Yi times P of X equal to X new divided by Y equal to Yi. Then for the denominator, you have for all the J for Yj. So because you're given a class label y equal to y1, y2. Okay, you have a set of yi's. So in this case, since in the numerator we already present this y subscript I, so in order to distinguish with numerator and the denominator, for the subscript we use the j. Okay, so subscript j. So you have to, for all class labels, you have to do all the computer probabilities. Okay, for the P of Y equal to Yj times P of X equal to X new, divided by Y, Y actually, Y equal to Yj. Okay, so this Y actually, this one, it's typo here. So in this case, we want to learn P of Y given by X is to use the training data to estimate the probability of P of X given by Y and P of Y, which is in the numerator, because in the denominator, we do the comparison because we wanted to compute the probability of Y equal to Yi given by X equal to X new. So we have the same denominator for each of the Yi's. Okay, because that one denominator is for all. So in this case, we can ignore the denominator because in all the cases, the denominator is a constant. So you can ignore it. So it is important for us to compute the two probabilities in the numerator. One is the probability of P of Y. So in specific, which is given by Yi. Another is the probability of P of X given by Y. So in the specific, P of X equal to X new and Y equal to Yi. Okay, so so from here, and this is the first one where it is important for us to have these two probability for the numerator. Use the estimation together and with the formula 1 and determine the P of Y given by X equal to X new for all the new data instance of X new. Okay, so what last time also we have discussed if you directly apply for the applying for the use the basis rule to apply in our case, which is in practical, because last time, so from here, the reason is stated here. So if you directly, we use the unbiased learning of the base classifier is impractical based on the reasons of, okay, so we want to compute, so from here, we want to compute P of X given by I, and we want to determine the number for training data instances for this computation for obtaining the probability. Okay, so in the simple case, we said if let's assume the y is a Boolean variable, so in this case, y just take two values, 0 or 1. Okay, now x is a vector of n features, so x is with the, okay, so the length, x is a vector with the length of n. Each of the x I in this vector, which is take the two attributes, okay, so infrequently, so for each of the x is also a Boolean variable. Now the total amount of possible parameters, which is 2 to the n times 2. Okay, so first let's see that x, since you have a vector of n, so each of the variable take the two values. Now the total amount of the combinations, which is 2 to the n. So you already go to the, okay, so in the case of computer architecture, and for the number of input, okay, so how can you construct a truth table, function table for the obtaining the function for the output? So in this case, we said, okay, so the input, okay, so how many inputs there? Each of the input is a binary, take the binary value either 0 or 1, okay? So how many inputs there? So you, for each of the inputs, take two value, 0 or 1. So how many input, which is 2 to the number of inputs. So from here, the same case, okay, 2 to the n. Now, since you have two class labels, you have to have two, because you see the other parameters, you have to consider, okay, class label, which is equal to 0, or class label equal to 1. You have to have extra these two. So total number of parameters, which is 2 to the n plus 1. Okay, 2 to n plus 1. Now, in the case of if x is vector containing 30 Boolean features, then we will need to estimate more than 3 billions of parameters, which is really impossible, impractical. Okay, impractical. So what are we going to do? And we have some conditional assumptions. Okay, based conditional assumptions. So that is the case of we apply basis rule. Our basis rule actually called naive base. Why naive base? This is the base. We derive our algorithm. We derive our algorithm based on some conditional assumption. Why need a conditional assumption? Because we have to shrink number of parameters. That is the reason. Okay, that is the reason. So in this case, okay, so here we have some examples to get a digest of what we have discussed in the previous. So we have toy data instances. So in that case, which is for each of the data instances, which is represented by a sequence of random variables. Now we have a feature, okay, so a feature vector with the size of 4. So in specific, we have x1, x2, x3, x4. So each of the features is a random variable. Take the value either 0 or 1, okay? Now we have a class label, okay? Y has two values, either 0 or 1, okay? So the number of parameters in order to compute the probability of P of X given by Y, first, based on, we don't have any, okay, this is an unbiased estimation. So we go to each of the axes. So in this case, so each of the axes has the value of 2. So how many such axes, which is 4? Now we have 2 to the 4 equal to 16. Then from, okay, so from y, we have 2 values, 0 or 1. So in this case, 16 times 2, which is 32. Okay, so total number of parameters, in order to handle this small toy data, you need 32 parameters. Okay, 32 parameters. So the other one is, I think I have the answer here. Okay, so this is annually I put there. Now, naive based algorithm. Okay, naive based algorithm. So since the number of parameters is as long as we don't consider some assumptions there, it is really impractical, because in the reality, we are not have the data set for each of the data instances, just only have 4 features. Okay, so in order to, you have to predict in the future for a new data instance. So in reality, so the data, okay, so number of the features need to be 10 or more. So in some cases, the number of features, if less, however, each of the features take a set of attributes. It is not just only one. In some cases, 10 and more attributes there. Okay, so so in this case, now we introduce the naive-based algorithm. So first we discuss the conditional independence assumption. So by the conditional independence assumption, then we apply whenever we have the basis rule in numerator, we can have some, based on assumption, we can simplify the computation, the number of parameters for the numerator. Okay, so we will see later in details. So the conditional assumption in general, it if we given a set of we give a set of 3 random variables. Okay, so from here a little bit typo there. We given a set of 3 random variables. These random variables represented by the x, y, z. We say x is conditionally independent of y given z, if and only if the probability distribution governing x is independent of value of y given by z. Mathematically, we can write down this formula. Okay, so for all I, j, k in the universe, for the probability, we have the probability of x equal to xi given by y equal to yj and z equal to zk is equal to if under the conditional independence assumption of the y given z, we do the computation of the probability of x given by x equal to xi given by z equal to zk. So in that case, we can ignore y, because there's no relationship between the y given y cost about the x. Okay, so here we have example which describe it is reasonable for this conditional independence assumption in a case. For example, we have 3 random variables to describe the current weather: rain, thunder, and light. Okay, so it might reasonable assert that thunder is independent of rain given lightning, because we know the lightning causes thunder. As long as you see the lightning, then you have the thunder. There's no information about the thunder is provided by the value of the rain. Okay, so that is the okay, one of the examples that we show our assumption, okay, is reasonable. Okay, is reasonable. Now, so from here, so the naive Bayes algorithm, actually, this is the case also in the weekend. I put this in. Okay, so if we compute the probability of x given by y, in specific x is represented by a sequence of x with subscript I. So we have x equal to, okay, so x1 to xn, which is a feature vector given by y. So under the conditional independence assumption, we can compute by this probability of x1, x2 to xn given by y, we can compute the product of the probabilities of each individual xi given by y. Okay, for I equal to 1 to n. Okay, so for each of the features in the data set, we want to obtaining a data instance x, which is represented by x1 to xn given by y. It can be based on the conditional independence assumption. We can compute the product of the probability of each of the individual xi given by y. Why it is the reason? So here is a proof. Actually, it is not required. I just showed to you the reason. So for the probability for each of them, if we don't have a conditional independence assumption, we just expand these probabilities of P of x1, x2 to xn given by y, which is exactly, we can compute the probability of x1 given by x2 to xn and y times the probability of x2 given by x3, xn, and xy times all the terms until the last term, which is p of xn given by y. This is the formula. We don't have the conditional independence assumption. So now you compute, you see, you check carefully for each of the terms for the probability. So for the x1 given a sequence of x's combined with y and y's, since each of the x's is independent of each other, there's not any relationship between these x's. Okay, so you can get rid of x's. You just put y there. Okay, based on what we have discussed in the previous slide. So for the x2 also, you have a sequence of x's and the sequence of x's and y. So since there's no relationship, we assume the conditional independence of these all x's. So in that case, you get rid of the x's, you're left of the y. For you do this for all, okay? So by this one, definitely, so it will give you probability of the p of x1, x2 to xn given by y can be computed as the p of x1 given by y times p of x2 given by y times p of 3, p of x3 given by y until times p of xn given by y. So this is the product of each of the individual of the xi given by y, okay, which is well represented in the box. Okay, we are presented in the box. Now, as long as we have this now, the parameters, number of parameters for us to request for the number of training instances, which is we can be tremendously reduced. Okay, so in this case, we have so this is the formula, okay, for the probability of x given by y. This is one of the terms in the numerator, okay, in the numerator. which is we started here. So in that case, we said we can have the condition independence assumption. So in this case, this is the case we have discussed in as the previous page for the example of the number of parameters we request. So the size of x, which is equal to n, each of the xi, which is equal to 2. The y, let's say we have 2 class labels. So number of parameters without conditional independence assumption to compute the probability of x given by y, in specific the probability of x1 to xn given by xy, which is equal to 2 to the n times 2 equal to 2 to the n plus 1. This is we already presented in the as the example, okay? So we cared about the advantages of if we have the conditional independence assumption. So the number of parameters in our case, it is equal to, since the probability of x given by y is a product of the individual probability of xi given by y for I equal to 1 to n. So in this case, the total number of possible parameters, which is 2 times n times 2, which is equal to 4 times n. Okay, be careful, remember it. In some books, they state it's just 2 times n. Why it is the case? Because we based on the probability, okay, probability function, the characteristic of the probability function, if we compute the probability of obtain the probability of a p, probability of q, which is equal to 1 minus p. Okay, but from this normal, for my case, for this case, I wanted to state it the normal way, which is the number of parameters is neither equal to 2 times n times 2. So first 2 is if we said we have if for each xi we have the 2, okay, 2 values, that is 2. So for the second term, n is the size of the feature vector, which is n, okay? For the last 2, which is the class label of the y, since we have 2 class labels, now we get 4 times n. So compare with there's no conditional independence assumption. Now conditional independence assumption, now the number of parameters is tremendously shrinked. Okay, tremendously shrinked. So here I want to remember this okay, difference. As long as you remember this difference, okay, so definitely you have the base there. Okay, so in most of the books, most of the cases, the professor discuss about the naive base. They just only introduce the formula. What is the reason? The naive base, which comes from, okay. So I describe this derivation here. By this one, now you're clearly, okay, you're clear why it is naive base. What when we want to reshrink the, okay. So however, this is and conditional independence assumption, okay. So that when you have to, okay, you have to be aware. Now we have example, okay. So this is example, toy example we described in the previously, okay. But this example actually use this example for the discussed advantages of naive base, which might be not appropriate because the result actually based on this computation will be the same. But you know, I just purposely wanted to show you the computation for the, okay, for the number of parameters and conditional independence assumption. But as long as you have a number of features increases, or for each of the values for each of the features the number of values for each of the features increases, definitely naive Bayes take the advantage. Okay, take the advantage. So in this case, so it is the toy example and the conditional independence assumption. So the total number of parameters to compute P of X given by Y, actually, so from here just only, so little bit, little bit smaller than what we already described. So in the case of we didn't make the conditional independence assumption, in that case, we have 2 to the n plus 1, 2 to the n plus 1, which is equal to 32. So in this case, the number of parameters, which is 2 times 4 times 2, okay, 2 is the value for each of the feature has the 2 values. 4 is the length number of the features, which is 4. 2 is the number of class labels, which is 2. Now is equal to 16. It shrink the half, but okay, if as long as the number of features increases, so the definitely you will see tremendously improved for the naive Bayes, okay, for the naive Bayes, for the which is and the conditional independence assumption. Okay, so so here we have another example for the, okay, still we use these 2 examples. We have the question and the conditional independence assumption. What are the 16 parameters? Okay, 16 parameters. So in this case, why I want to have these questions in your quiz 3, I asked you to have some computation, okay? So for the number for parameters, okay, so in this case, as long as you get the idea, you know exactly the number of parameters. So in your homework assignment, okay, so homework assignment 1 or 2, so in that case, there's no problem for, okay, there's no problem for. So let's see, we already used, okay, we end the conditional independence assumption. We have number of parameters, which is equal to 16. Now, what is 16 exactly? Okay, what is 16 exactly? So in that case, actually here it is a computation, okay, so which is, it is 16 parameters, okay. So in specific, we have a probability of X is equal to X1, or X, so in this case, X, which is equal to X1, the value of the X1 is equal to 0, okay? So, and the class label Y is equal to 0. So in this case, we have class label Y, take okay, 2 class labels, we have 0, 1. For the each of the X's, we have binary variable, so take the 0 or 1. So this is the number of parameters we discussed in details. So we have X1 equal to 0 and Y given Y equal to 0. X2, so from here, X1 equal to 0 given Y equal to 1. X1 equal to 1 given Y equal to 0. X1 equal to 1 given Y equal to 1. Okay, so for each of X's has 2 values, and these 2 values you have 2 class labels. Okay, you have 2 class labels. So this is 4 cases. Now, since you have 4 class, or since we have 4 features, for each of the features, you have to do these probabilities. Okay, probabilities. So for the X2 equal to 0 and the Y equal to 0, X2 equal to 0 and the Y equal to 1, X2 equal to 1 and the Y equal to 0, x2 equal to 1 and y equal to 1. Okay, you do x3, x4. You have to have these all the cases. Okay, so you have so this is the 16 parameters in this specific data. Okay, specific data, and you have to do this all computation because later on you have to use these parameters to predict a new data instance. You don't know what new data instance is. You have to prepare for all the cases. Okay, you have to prepare for all the cases. So this is for the, okay, so the example of all the 16 parameters and based on this toy data set. Okay, data set. Okay, so here we still, okay, so we discuss a lot now. It is the chance, it is time for us to go to our, okay, so go to the data set in general, okay, describe the naive Bayes algorithm, okay. So naive Bayes algorithm, again, which is based on the basis formula. Now, based on the basis formula, we expanded to the data in the specific, then we find we have some difficulties there. And because it need, okay, this tremendous amount of parameters, we cannot afford, we cannot standard for this. So what are we going to do? We make some conditional independence assumption. By this conditional independence assumption, we tremendously reduce the number of parameters. Okay, so so this kind of algorithm we based on the basis loop, but we add some conditional independence assumption. So this kind of algorithm we call the naive Bayes algorithm. Okay, naive Bayes algorithm. Now let's go to this naive Bayes algorithm on our, okay, on our data set. Okay, in so let y be a discrete value, the variable, and x be the any data instances, which is represented by x1 to xn. The goal, we need the chain classifier that will output the probability distribution over the possible value of the y for each of the data instances that we ask it to classify. So we, okay, so the purpose is we want to predict the class label of a new data instance. As long as we obtain a new data instance, so how can compute the probability? How can predict the class label of that new data instance? Now, you definitely based on what you have seen from data set in your hand, that data set for each of the data instances has a class label there. Now then, based on these class labels, you can compute the probabilities we call the parameters. So by these parameters, we can predict, okay, a new data instance. Okay, a new data instance. So that one is our goal. Okay, so that one is our goal. So now in specific way, so these two formula in two boxes, the first formula is based on the basis rule. The second formula is naive Bayes algorithm is based on the conditional independence assumption, because the one of the terms in the numerator in specific, it is P of the x1 to xn given by y equal to yk is represent the product of the P of individual xi given by y equal to yk for all I is equal to 1 to n. Okay, so the difference between these two, the formula in these two boxes is the second one is n the conditional independence assumption, which is the algorithm we're going to use. Okay, so naive Bayes algorithm. Now, So for the naive Bayes algorithm, actually, we just copy in the in the second formula in the previous page. We just copy down. So we added something there. So in this case, we just see the numerator. Okay, so for numerator. So in this case, we said we compute the probability for specific class label called YK. Actually, we need to try all the YKs for the probability. Okay, for the probability of all the YKs, we select a class label YK such that the probability is the largest. So we assign that class label to the data instance X. Okay, data instance X. That one is we focused on. That one we call the naive Bayes. Okay. So again, so the denominator does not affect our decision because for each of the J's, the denominator are the same. So it is not affect our computation to obtaining the class label YK. It yield the probability of P of Y given by X, which is a posterior probability, which is the largest. Okay, so we get rid of the denominator. So specifically, the naive Bayes classify, which is train your data set based on the naive Bayes algorithm, which is represented by here. We, in order to compute the probability of Y class label Y given under the data instance X, which can be computed by class label, computed by the P of Y in specific for YK, then we times the product of the individual probability for each of the feature Xi's given by YK for I equal to 1 to N. So we do this for all the class labels for YK. For example, if we have Y, okay, we have 1, 2, 3, you have to compute for these all class labels. Now you select, you compute this order, you have the probability there. So you have 3 probabilities there, yielded by each of the class label YK. So you select, you assign that YK to the data instance X such that the probability of Y given by under this X, which is the largest. Okay, from our case, we don't set up the threshold, we just only amount of these probabilities we select, we assign the class label. So that class label yield the largest posterior probability. Okay, a posterior probability. So that one is a naive Bayes. Okay, so we, okay, so a naive Bayes classify. So naive Bayes classify is you apply naive Bayes algorithm on your data set. Then by that data set, you have a set of parameters. And so actually this naive Bayes classify, because you have to use this set of parameters to predict the class label for new data instance. Okay, this naive Bayes classify, which is you apply naive Bayes algorithm on data set, you train a set of parameters. So naive Bayes classify, which is represented by the set of parameters. Okay. Okay, so that one is the naive Bayes classify. Okay, so but you might ask actually, okay, I have several minutes. Let me do this for the discrete value, the input. So next time I still will start from this this page. So actually for each of the features, we have 2 kind of situations we need to handle. Okay, 2 kind of situations we need to handle. One is each of the features take the discrete value. Okay, for example, if you have a binary feature, take the 0 or 1. So in that case, you have a feature, take the discrete value. But in some cases, you have a feature, now take the continuous value. This means you do the statistics. You have maybe thousands of, hundreds of thousands of values for and some feature. So this kind of a feature, how can handle it? How can compute the probability? How can have the statistics? This is the issues we have to discuss. Okay, so when is for the discrete value, the input, this means for each of the features, the value for each of the features is discrete. Okay, discrete. So we also will describe a continuous value, the input. Okay, so we will describe it later. Okay, so we want to do the computation. We want to do the statistics. Okay, for the features which you take the discrete value. Okay, we will take the discrete value. So this is for the how can do the computation. Actually, I cannot finish this one. So next time I continue start from this page, then I will describe the method. Actually, if you have two kinds of estimation, one called the maximum likelihood estimation, another called the maximum a posterior probability estimation. Okay, so actually this kind of a value, how can do the statistics is based on one of the method. Frequently, even we don't say it, actually, frequently we use the maximum likelihood estimation. Okay, so for the statistics. Okay, so actually the time is just only a minute left, so I will stop the recorder.